Good evening, everybody. So, in this lecture, we discuss on the fourth zone of the boundary layer, that is laminar sublayer. In the previous class, we discussed about the laminar boundary layer, transition, turbulent boundary layer. Within the turbulent boundary layer, adjacent to the boundary, there is a small zone where the flow exhibits the characteristics of laminar flow. We call it as laminar sublayer. In this laminar sublayer, the velocity distribution is parabolic. However, as the zone thickness is so small that we consider the velocity distribution as linear, and the equation for the shear stress, Newton's law of viscosity, tau naught is equal to mu into dv by dy is applicable in this region. Second point is why we are studying this laminar sublayer. What is the significance of laminar sublayer? The significance of laminar sublayer is if you want to classify the pipe boundary, the pipe inside boundary, whether it is hydrodynamically smooth or rough. If you want to classify it, you must know what is laminar sublayer. So that context also you should remember. Then again, next question, why we should know whether the pipe is hydrodynamically smooth or rough? Because depending upon whether the pipe is hydrodynamically smooth or rough, naturally the resistance or the losses will be high. In the case of rough pipe, the losses are very high. Whereas in the case of hydrodynamically smooth pipe, naturally the losses will be less. Because any pipe, even new pipe, if you put it after some time, the inside, if you take it inside the pipe, always the roughness projections will come out. As long as these roughness projections are within limits compared to the laminar sublayer, the damage is very minimal. But if the roughness projections height is more, then their damage is more. So this is the first topic which we are working on. Once laminar sublayer is completed, that completes for us all the zones of the boundary layer. The next one is what is the separation of flow, separation of boundary layer. So the separation of boundary layer generally occurs in the presence of a positive pressure gradient. The positive pressure gradient leads to finally the separation of boundary layer, which is really a negative phenomenon because the separation of flow always leads to more and more losses. So we do not want separation to take place. But in some cases, separation occurs. When it occurs, then to avoid separation, what should we do? What are the methods that we follow to avoid this separation? So that will be the last. So three topics we have for today's discussion. One is laminar sublayer, its significance. Second one is you're taking up separation of boundary layer. Last one is how to avoid separation of boundary layer. Let us take straight away into the question. So today's topics laminar sublayer, separation of boundary layer, measures to avoid separation. So these are the three topics. So let me go take up first laminar supply. If you draw the growth of the boundary layer on a flat plate, so if this is the flat plate, the boundary layer starts from leading edge, transition. So this is LBL, transition, TBL. Within the turbulent boundary layer, adjacent to the boundary, there is a small, this is called as laminar sublayer. This is what I mean. Right? Now we are interested to study about this region. What is this region? So that means if the plate is very smooth, that even in the zone of, even in zone of turbulent boundary layer, there exists a very thin layer adjacent to the boundary. Very, very important word. Adjacent to the boundary. In this layer, the flow is laminar. This layer is called laminar sublayer. Then coming to next, the thickness of laminar sublayer is denoted by delta dash. Please note that, right? Already I mentioned the flow in the laminar sublayer. The flow exhibits characteristics of laminar flow. Velocity distribution is parabolic. However, as the thickness is so small, we take it as linear. Right? Next. In laminar sublayer, tau naught is equal to mu into dy by dy is applicable. Then what is the equation for delta dash is equal to 11.6 into nu by v star. And this equation is given by Nicorot. What is v star is called as shear velocity, which is equal to root tau naught by rho. And nu is nothing but kinematic viscosity. is the application of laminar sublayer to determine whether the boundary is hydrodynamically smooth or rough. This is the application. Any, whether it is pipe or plate, whatever it is, the inside boundary where it is subjected to the flow, that boundary. For example, if I take it, this is the boundary. Now, these are all the roughness projections. The roughness projections. What is this? These are all the roughness projections. If I take the average height, it may be some K. Suppose now I take, this is how the laminar sublayer is. This is what? Laminar sublayer. So now if you observe, basically, all the roughness projections are below the laminar sublayer, right? All the roughness projections are well within laminar sublayer. Or in other words, LSL is much above the roughness projections. Such a pipe is called as hydrodynamically smooth because the roughness projections are not exposed at all. They are being completely covered by laminar sublayer. Then we call that pipe boundary as a smooth boundary. Right? And for hydrodynamically smooth boundary, it is basically the V star into K by nu is less than 5. Here, what is V star? V star is equal to shear velocity, which is equal to root of tau naught by rho. K is roughness height. Nu is kinematic viscosity. The other case I will take you here itself. Suppose there is another boundary, right? Here the projections are like this. This is the thing. Suppose now I take it, the laminar sublayer is like this. Now, if you see here, the roughness projections, the roughness projections penetrate through laminar sublayer and directly exposed to flow. Here the flow is above it. Here the flow is not, the roughness projections are not subjected to flow because laminar sublayer is protecting them. Here, the roughness projections penetrate through laminar sublayer and directly expose it to the flow. Such a pipe is called as hydrodynamically rough. Such a boundary is called as rough boundary. Rough boundary. For it, it is V star K by nu is greater than 70. Remain notation holds good. So how the figures you check it up. This completes one article. What is hydrodynamically smooth? Then we will take up what is boundary layer separation. The boundary layer is affected by the pressure gradient. When I say boundary layer means boundary layer thickness is affected by the pressure gradient. If suppose the pressure gradient is negative, it is negative, then what happens? Pressure is decreasing. Pressure is decreasing means velocity is increasing. When velocity is increasing, the boundary layer thickness decreases. This is when dou p by dou x is equal to 0. Again, boundary layer thickness grows steadily. If dou p by dou x is greater than 0, this is called as adverse pressure gradient. The boundary layer thickness increases rapidly. Increases rapidly. So therefore, conclusion is the presence of positive pressure gradient or adverse pressure gradient increases the thickness of boundary layer. The adverse are positive, both same. Adverse pressure gradient plus the boundary shear the boundary shear decreases the momentum of flow. What they will do? Decreases the momentum of flow because positive pressure gradient means what is the meaning? Pressure is increasing. Pressure is increasing from point to point. That means velocity is decreasing. Velocity is decreasing means actually that's what I'm telling. Velocity decrease means automatically the thickness of the boundary layer should increase. This you should. Momentum of flow in the boundary layer decreases. Decreases basically. And if both of them acts over a basically sufficient distance, boundary layer separation This is the reason. Right? This phenomenon is called separation. Main reason I told for separation, there are two things: adverse pressure gradient plus bond ratio. These two together, actually, if they act separation, it leads to separation. This is the concluding point. So now I take an example. For example, you take a curved surface. A curved surface, if you imagine, and another surface also you can imagine like this. This is how the flow takes place. When the flow is taking place here, if I take a point A here, this is how the flow is. If I take a thing, how the velocity distribution is, if I see, this is how the velocity. Then if I go to another point B, it becoming uniform actually. It is becoming almost like a uniform. Suppose if I take a point here, C, almost same, right? Beyond C, if I take a point on the downstream, what I observed is this is how the velocity distribution is. Exactly at this point, the flow gets separated. This is what is happening. And once flow gets separated, if I take any point E here, for example, when I observe it here, what happens actually, if I see here, velocity distribution is like this. And one more point is here, there is a cross flow. This is cross flow. And this one is the separation of boundary. My question is where this separation occurs. If I take in this from A to B, B to C, whole thing is, if I see, pressure gradient is negative. Here up to A to C, if I take it, pressure gradient is, for it is an accelerating flow because velocity increases. But if you take a point basically, for example, from C to D to E, if you take this is pressure gradient is positive, then it is decelerating flow. If I see this actually slowly at a distance, right? At a distance from C on downstream side towards DE, the fluid near the boundary near the boundary surface is brought to rest, is brought to rest. Here, the velocity gradient dou v by dou y is equal to 0. This point is called separation point, that is D. At separation, there are two things. Pressure gradient is equal to positive. Dou v by dou y is equal to velocity gradient is equal to 0. On the downstream of D, beyond D I am going. Further retardation of fluid close to the boundary cause reverse flow, that is precisely at E we have shown. As a result of reverse flow, what is the problem if reverse flow? Reverse flow, as a result of reverse flow, large cross currents, which is also called as eddies. Eddies are nothing but losses actually. Large cross currents, eddies, are formed in which energy dissipation is high in the form of heat. This is the next point. Separation occurs both in laminar boundary layer, turbulent boundary. But laminar boundary layer, basically, laminar boundary layer is, is vulnerable for separation. Right? Next thing is the separation of boundary layer greatly affects the flow. Greatly affects the flow. Separation creates a zone of disturbed fluid. What it does, a zone of disturbed fluid, thereby creates pressure difference and ultimately pressure drag. Separation gives rise to more resistance, more loss. Every attempt should be made to avoid separation. So this completes the next. Next article is prevention of this operation. Methods of preventing separation. What are the various methods? Number one, streamlining of body shapes. What do you mean by that? This is what we call it as streamlined body. Now, if the flow is taking place, this is how the flow takes place. So it is parallel to basically as good as the streamlines. So this is our body. The body shape is such that it is streamlined. So flow takes place over it. These are all the flow lines. These are all streamlines. So this is what we call it as streamlined body. So this is one. Number two, number two is basically the rotating boundary. In any fluid flow problem, rotating boundary actually results in the avoiding separation. Rotating boundary in the direction of flow. Suppose you are having a cylinder. Take the cylinder perpendicular to the board. So if this is the body, now what is expected from us? This body is to be rotated like this. If it is rotated, then the flow will be so this is a rotating cylinder. These are all streamlines. Third one is accelerating the fluid, accelerating the fluid in boundary layer. Fourth one is actually providing guide blades in the bend. Fifth point is providing a bypass in slotted wing. What is that? You make the shape of the body. So this is the body. What you are asked to do, you make actually a slotted thing opening here, right? If you make this naturally when the flow take place, if the flow takes place like this, then naturally the flow can move from this direction to this direction also. So this is what we call it as slotted wing. Then you can have injection of fluid into the boundary, into the boundary. So how to do it? For example, if I take it, right? If you take it from here, injecting the fluid into the thing so that the flow never gets separated. Make it the flow as velocity higher. So that is the objective of doing all the things. So from here, the fluid enters. So this is what we call it as injection of fluid. This is one method. Then another method like this, suction of fluid, suction of fluid from boundary. This is another method. Again, the same thing, right? Suppose when the flow is taking place, certain flow takes place inside. So these are all flow lines. So suction, the making it, this is sucking, suction. So these are the various methods to avoid separation. All these methods, the basic principle is increasing the velocity. That means whether by adding discharge you can do it, or by rotating the cylinder you can do it, or streamlining the body shape you can do it, providing suction of the fluid you can do it, injection of the fluid you can do it, by slotted wing you can do it. So this completes to us the one of the one of the most important topic of laminar sublayer.
Like, share, and subscribe. Hit the bell icon for more updates.